Okay, so we've talked about electric potential, and then we talked about potential difference, and then we said potential difference is also known as voltage. Well, voltage we associate with batteries. So today we're going to talk about batteries, okay? We're going to start by just kind of going through what we finished off with, though. We've got a capacitor, a plate that's positively charged, it has higher potential, a plate that's negatively charged and it has a lower electric potential. And then we said that the change in potential, or the potential difference, is also called the voltage. All right, so let's go ahead and make ourselves a battery. Well, a simple battery consists of a box. So here's our box, okay? And then inside that box, we are going to put an electrolyte, okay? In this case, we're going to make it sulfuric acid. So we've got some H2SO4, some sulfuric acid in here, okay? And then we're going to go ahead and place 2 electrodes inside of this, okay? We'll have one electrode made of carbon and the other one made of zinc. What happens is the zinc electrode is going to react with the sulfuric acid, okay? And when it does so as an ion. And these ions have a positive 2 charge. So that means that the positive 2 charge is coming out here, and the zinc is going to be left with an overall negative charge, okay? Now, the part of this electrode that sticks out at the top is called the terminal, okay? Now, while this zinc is reacting, carbon's going to have a reaction as well. It's reacting with the slightly positively charged sulfuric acid now, this electrolyte, and it's leaving the carbon with an overall net positive charge, okay? And this is similar to these 2 plates, okay? We've got a positive terminal and a negative terminal. The positive terminal has a higher potential. The negative terminal has a lower potential. So we can now talk about the potential difference, also known as the voltage. Now, let's come back over here. If I stick an electron in this field, the electron is going to move toward the higher potential because opposites attract. Okay? So in this situation, we need to put some electrons. Now, a misconception is a battery is just a bunch of electrons. It's filled with electrons, and the electrons leave and come out, and they go around, and that's what gives us the electricity. And unfortunately, that's just a very big misconception. Okay? If I attach a light bulb to this, okay, the light bulb already has electrons in its filaments and in the wires that I'm using to attach, okay? And it's not any electrons that are just jumping out and leaving, okay? What's happening is the electrons that are already in this filament and already in this wire are now in this space where there's a potential difference, and so those electrons are going to be drawn towards the higher potential. Okay, another thing I want to go ahead and do is just review, because there's a lot of things that sound alike, that look alike. Okay, our equations all are kind of similar. So let's go ahead and review a little bit. We started off talking about forces, okay, the electric force, and then we started talking about the electric field, and we moved on to electrical potential energy, and then finally just electric potential. Okay, well, the electric force has the equation. The electric force is equal to Coulomb's constant times charge 1 times charge 2 divided by the distance between the charges squared. And it's a force, and it's measured in newtons. Okay? And then the electric field has the equation. The electric field is equal to Coulomb's constant times the charge divided by the distance away squared. These two are both vectors. Okay? And so, with a vector, we are not going to include the negatives. In the equation. Instead, when we're done, we are going to add the direction. We're going to include the direction. Okay, so this vector column, we don't include the negatives in the equations, but we do include a direction, and these are vectors. And then if we look at the potential energy, well, the potential energy equation looks a whole lot like the force equation, okay, Q1 over Q2, only we're only dividing by the distance instead of the distance squared, okay? And the electric potential looks a whole lot like the field equation, except that it's just divided by the distance, the distance, not the distance squared, okay? These are scalars, okay? Potential energy and the electric potential are scalars, which means we do include the negatives for our charges, but there is no direction. Okay? There's a lot of things that look and sound alike, okay? But forces measured in newtons, fields measured in newtons per coulomb, okay? Both vectors, we don't include the negative in the equation, instead we have the direction at the end. Then we've got potential energy, which is an energy, so it's measured in joules. And then we have potential difference, which is a joule per a coulomb, which is a volt, okay? And these are scalars, so we do need to include the negatives in here, but we do not include a direction.